Good afternoon, everyone. We are the L3 Mass Spring Damper Project. Our team consists of Zach, Chandler, Mike, Holly, Ryan, and I'm Anthony. Before our project, L3 theorized a mass spring damper system to filter vibrations from their product. As you can see in Figure 1, their original mass spring damper system was really large and really expensive. There's a lot of material to it. And most of the input work that they did for our project was just designed for application of our project, what they could do once our project was realized. So as far as L3 Harris was concerned, we were tasked with creating a mass spring damper system to filter out vibrations. And we were also tasked with determining the feasibility of such a system. And lastly, we were asked to design a method for selecting the material properties of the flex circuits that we were going to use.
And so we didn't want to take an iterative approach where we ordered and tested because we figured that would take too much time. And so we used 1D and 2D models, FEA and Matlab Code to go ahead and develop and predict where a starting point would be in order to get a frequency under 2000 hertz dampening such that we could get a project that they wanted. And so to start, we went ahead and created a Matlab code assuming that our flex circuit of 4 springs could be modeled into in a series. We assumed massless, and we only wanted to take into account the horizontal motion of our vibrations. So we used the rule of mixtures to go ahead and approximate our Young's modulus for this because we didn't have a known modulus prior, and from our literature, it looked like it held true pretty well. We then went and found a forum on Science Direct using Castellano's theorem, where we model these springs as semicircles and apply a force load on the top and get a spring constant, K value, to go ahead and understand the dynamic response of our system to ultimately predict the natural frequency of our system. From there, we went ahead and did a 2D FEA abacus model to see how well Castellano's theorem matched what we were doing. And we went ahead and found a verification of the highest difference being 0.05% between Castellano's and our 2D FEA. So we went ahead and used that to calculate our K values in the Matlab code. From there, we went ahead and we developed 2 orders. Order 1 to go ahead and test the Young's modulus theorem to see whether or not that actually holds true and is valid for our project, the rule of mixtures. And then we also did a test. We hoped to do a test on compression to see how well K related to the 2D FEA and Castellano's theorem, but this was not able to be performed because we ran out of lab space with the virus happening. Order 2 came in, and we went ahead and created a dynamic response to test on a shaker table to actually see how well the natural frequency matched the 1D code for our horizontal component.
Okay, so as Ryan mentioned, we performed 3 tests for the project. The first test was the tensile test, which we conducted on flex circuit test strips. We did this to get the Young's modulus of the material. To do this, we designed and ordered 6 different types of dog bone samples to test. We varied the copper content, and when we vary the copper content, we also vary the stiffness of the flex material. And we also chose to do a linear uniform layout of the copper. This simplified our equations in the long run. Chandler will talk more about this test in a little bit. Our second test that we performed was our pilot test, where we built 3 mock prototypes to test on the shaker table. So we decided to build these prototypes because the material shipment from China was delayed due to the coronavirus. So we wanted to have some sort of backup plan to be able to start testing. So as you can see in figure 3, there's one of our mock prototypes. We built 3 of them. So to build the prototypes, we 3D printed using a PLA filament, and these 3D printed parts were then used as to simulate the PCB material of the prototype. And for the flex circuit stack up portion, we used a combination of Kapton tape and copper tape. And as I mentioned earlier, we built 3 of these. So we varied the copper and dielectric ratios between the 3 of them. So we had a 25% ratio, a 43, and a 60%. And as I mentioned earlier, we wanted to have this test as a backup plan, but the main goal of this test really was to verify that the shaker table, the test setup, the software, we're all communicating and working properly together before we actually got our material. Mike is going to talk later about the test setup for the shaker table, and Zach is going to be talking about the results that we found in the pilot test, which actually proved to be really valuable to our overall process. And the last test that we ran was on the actual manufactured prototypes using the shaker table. And we worked with L3 engineers to design and order these 8 different prototypes, each varied in copper dielectric ratio, as I mentioned earlier. And then in figure 4, you can see our prototype G. It has a 25% copper to dielectric ratio with a width 3/4 of an inch and a length just over 1.5 inches. And the thickness of the flex material is 14 mils. And Zach is going to talk a little bit later about the results of the response data that we found through this test.
Cool. Like Holly and Ryan said, I'm just going to talk a little bit more about the tensile testing and why we did it. Tensile testing is a way for us to validate how we were going to fine tune the natural frequency for our prototypes. We knew that we could change the width of our prototypes, we could change the length of the arms on the prototypes, or we could change mechanical properties such as Young's modulus. And so we wanted a way to validate that we were accurately changing and controlling the Young's modulus within our prototypes. So like Holly said, we got these dog bone specimens, we drew them up in AutoCAD and then sent them over and had them manufactured. We made 5 different specimens and we made 3 replicas of each of them. And then we ran them on we put them in an Instron machine to get their Young's modulus. And we wanted to compare that to our theoretical value that we got from the rule of mixtures. The rule of mixtures, just a brief description if you don't know what it is. Basically, it's a way to take a composite material and find the large dominating materials in it and relate their percentage that they make up of the composite and how it contributes to the Young's modulus. So if you have a 60% copper specimen, you take 60% of the Young's modulus of copper and you add it to the 40% of dielectric times by its Young's modulus. After running the results from the Instron machine and comparing it to our theoretical values, we were actually pretty close to predicting the value that we wanted. It was more accurate with a higher content of copper. So our black line right here was within a 4% difference. As we moved down, this blue line was 20% difference from our theoretical value. The other key thing that we learned from tensile testing, and this is kind of in hindsight, we were expecting a value of a Young's modulus from our dog bone specimens to be upwards of around 120 GPa, because that's what pure copper is. But after doing it, it was closer to the magnitude of 10 GPa. This sparked us to investigate the copper material used a little bit more. And what they do is they anneal the copper before they put it in the PCB boards. That annealing process changes the copper Young's modulus drastically from, like I said, 120 closer to around 10 to 15. So that was a really key thing that we learned from the tensile testing, and I was able to get with Ryan and run some codes, or run those values through his code again. Now Mike is going to go ahead and talk about our shaker table test.
So the shaker table, L3 they had made it in-house as a project to do active vibration cancellation. And we were able to repurpose this test equipment to do shaking in just the Z direction only using a singular piezoelectric actuator. This shaker table is controlled by a data acquisition unit running M+P analyzer software. From this, I'm actually going to give a demonstration of the shaker table, and I'll talk about the different components of it. So right here's our test setup. We have the laptop, which controls the data acquisition unit, a power supply feeding an amplifier that runs the shaker table. On the shaker table, we have a accelerometer right here for the reading the input of the table, and then we have the accelerometer on the prototype that reads the response from that. As Holly mentioned earlier, we did some prototypes, hand-built prototypes. That's these items right here with 3D printed parts, copper and capped on tape. We also made the mounting plates for them. Here's the prototypes, the manufactured prototypes as well. And they come in a sheet, a full sheet, and each one of these has varying copper contents as well as dimensions. With that, I'm actually just going to run a quick demo on the shaker table. We'd set up a quick test profile to show how this works of about 5 seconds long, doing a random vibration of 20 to 2000 hertz. So here on the software, I'll just hit start, and it will start the shaker table. And with this shaker table, it has very small amplitude. It's only about 350 micrometers, which is, has been sufficient for gathering data and showing that our prototype does reduce the vibrations on the prototype. And with this, I will go back to the poster board, and Zach will talk about the test data.
All right, thanks, Mike. So basically from that shaker table, we were able to first gather a bunch of pilot data, which informed us a lot about the uses of the shaker table. So we actually went through testing our mock prototypes and moved on to even testing some of the manufactured prototypes. And from that, we gathered valuable information. And the most valuable one was that our data that was being gathered was very poor. And we needed to figure out what was going wrong so we could actually read the values we wanted. And one of the main reasons that we had poor data at first is we were testing between a range of around 0 hertz to 20 kilohertz, which in reality, we only wanted to see things maybe between 0 to 300 hertz or even lower. So we ended up with extremely low resolution in between the values of the hertz, because the table is just not able to gather data in that big of a range in a very fine way. And so once we discovered that and was able to figure out how to run the test profile, we only had time to run one of our manufactured prototypes, which was prototype G, and the specification can be seen down in table 1 for that. So once we had that profile, we started running the data, and you can see the main data for it in figure 6 and figure 7. We ended up running 2 different types of tests on it. One was a 1G sine sweep, and the other was a random vibration test. So from starting with the 1G sine sweep, you can see the first things you see is the peaks coming on at 25 hertz and 50 hertz. We believe this to be the resonant frequencies of our actual testing fixture, or the table we were actually working with. We believe that's kind of what's going on there. But you can notice there's a difference on the top of this 1G sine sweep. we're plotting the actual table response. And on the bottom in green, we're actually plotting the prototype response. So in this response, you can actually see that we're seeing something like 60 hertz, and then there's also a little blip that comes along around 180 hertz. Now, from the Matlab code that you've heard talked about before, we were actually predicting that this prototype G would end up with a natural frequency of 53 hertz, which is very heartening because we found in our data that there's a spike around 60 hertz. Then moving on to the random vibration testing, we have we found a very similar type of thing. There is some type of peak going on in attenuation around 60 hertz, but there's also another portion of attenuation going around 150 hertz. So the 150 hertz, that one may correspond to what was going on at maybe the 175. Maybe I'm just not zooming in close enough. So this was good because it kind of showed that our design and our predictions were sort of matching with each other, but there still needs to be more testing involved in this. We've only been able to do the refined testing on one of our prototypes, the G, but we still need to do the other A through H. And to add more confidence to it, we actually wanted to do something more like an impact test, because if we can get the same type of results from coming at a different way, we can help to confirm that the predictions we're making and the results we're getting are actually valid, and maybe it can actually inform other people in the performance of these little prototypes.
So as you can see, we were successful with our limited data in creating a mass spring damper system that filters out vibrations using flex circuits. And we were also successful in being able to predict the natural frequency to a relative degree of accuracy using the material properties of this, the spring constant and Young's modulus for each of the flexes by varying the copper content. And looking forward, in order for us to be positive that our results are correct, we would need to continue our tests with the rest of our prototypes. It would also be beneficial to do an impact test, like Zach was saying, and compression tests like we had originally intentioned to predict values. So, thank you. Are there any questions?